Hi, everybody. I'm Jesse Wilson, and this presentation is called Nerding Out on OKIO. And I don't really have like an overall coherent agenda. What I just wanted to do was go through the OKIO library in like a really sort of like deep way and not necessarily uniformly. I'm just going to talk about a whole bunch of things that I think are cool about OKIO. And I hope you enjoy because I think it's there's lots of cool, fun stuff. So I said fun stuff. OKIO is a really fun library to work on because it's got both computer science, software engineering. It's widely deployed, and brazen is like a weird word where we're being opinionated in this library. I'm going to go through these points again. In university or college, you probably took computer science. And this is like really sort of like theoretical and mathematical. And often, the only time that computer science really comes up in my job is when people are interviewing and it's like, okay, let's ask algorithm problems because algorithm problems are fun, but they're not that related to the work that we do. Whereas software engineering is like, how do we actually build software that works, is reliable, is reproducible, we can develop it continuously. And so OKIO is fun because we have both the computer science aspect of it, where I'm going to talk about a bunch of data structure and algorithms in the library. But there's also a whole like real applied part of it where this library is in use in a whole bunch of different projects. And it's important that like we get our API evolution correct. OKIO is really widely deployed. This is a screenshot from AppBrain. And you can see that it says total number of downloads, 322 billion. That's something that I could tell my mom about. That's a lot of billion. And so chances are on your device, in addition to having like the OKIO that's baked into the Android OS, you probably have a handful of applications that also have copies of OKIO embedded in them. Anything that's using retrofit OkHttp coil, Apollo, Moshi, Wire, all those things have transitive dependencies on OKIO. And brazen, it's like, why the heck would you build an OKIO? Java already has a perfectly good IO library called Java IO. And if you don't think that's good enough, well, it's already got a good replacement called java.nio. OKIO is a blocking library in the era of non-blocking libraries, things like Netty and Vertex. And we switched to Kotlin in 2018. That was a really sort of surprising thing to do, to take a library that already has billions of downloads and billions or hundreds of thousands of applications using it, and to change which programming language is implemented in. And we did it. And in hindsight, it was the right call. But we're not going to be completely wild with what changes we make. It just seemed that one was a bit ambitious, and we tried to push the Kotlin multi-platform ecosystem forward. So IO. Okay, it was an IO library. Let's talk about IO. Java IO is the IO you probably maybe learned in school, and you'll interact with it a lot as an Android developer. I'm thinking of IO in this talk as sort of like destinations. Where do I want to get the data? And it's often a file or a socket, which is just a lower level way to get to a web server. Roads or the transports, so you get that data from the file via an input stream or via write it to the file via an output stream, and then the data travels sort of through these streams in bytes or byte arrays. And so if you look at like the socket interface, it just gives you two streams, and the stream APIs are really focused on byte arrays. Byte arrays are sort of like the fundamental currency of Java IO. If you want to read anything, you say, hey, input stream, here is my byte array that I own. Fill it full of your data. Or if you want to write something, you say, hey, output stream, here is my data. Copy it to my destination. And so we weren't setting out to build OKIO. We were working on this project OkHttp, and we ended up needing IO. And I want to talk a bit about how this all sort of came to be. The beginning, OkHttp's job was relatively easy. The caller of our API says, here's an HTTP request. And we need to take the headers and the method and the path and everything and encode it into something we can send on the socket, a byte array. and then take that byte array and transmit it to the remote web server on output stream. The server is going to take our request, interpret it, process it, and return a response. We'll get that as a byte array from the socket's input stream, and then we'll transform that input stream back into an HTTP response. It's like how hard is this job? It looks like it should be relatively straightforward. When we added an HTTP 2, things got a little bit more complicated. In particular, this sort of like direct relationship between the inputs and the outputs gets a bit more complicated. So we take the inbound HTTP request and we chop it into frames. So, you know, each request, depending on its size, may be many, many frames. Then we write those to the output stream. And then on the input stream, the way back from the server, we don't get like the response as a single object. Instead, we get different frames or different chunks of the HTTP response. And we have to assemble them, and intermixed with the frames of my response might be, you know, the frames of some other response that the application is currently performing. And this gets complicated. In particular, we end up with an interface that kind of looks like this somewhere inside of OkHttp. We have a map of all the in-flight HTTP calls, which I'm calling streams here. And then we have some active thread that's just reading all the data from the inbound network and figuring out who gets what frame. So if it gets a frame from the network, it figures out which stream owns it, and then says like, hey, stream, here's some data for you arrived. And so we end up with an interface a little bit like this inside of OkHttp, where we receive some data, and then independently at some other time in the, you know, maybe has already happened or will happen in the future, is the calling code will say, hey, I would like to read some of the data from the server. And this may block waiting for that data to arrive, or the data may have already been there and we would have needed to store it. And so this is the sort of like API that is sort of comes about out of building HTTP 2. We need some way to stash the data from the server and bridge these two sort of actors, one being the thread that's servicing the network and another being your application thread. And so if we want to go implement that interface, we need to build some buffer, something where we can store the data. And so I'm going to go through a bunch of the different candidates that we can do as like, just how do we implement this thing? And so imagine that we say, we're going to implement that interface as just a list of bytes. And so this is kind of what this interface would look like. I'm going to draw the buffer interface as something that has a write function that receives bytes. In OkHttp's HTTP2 case, this would be receiving bytes from the network. And then some other call to read those bytes that were stored in the buffer. And in both of these cases, I'm following the Java IO sort of standard, where the caller is going to always give me their byte array. And my job is to either put data into it or take data out of it. And so we get this like relatively straightforward interface. I just love how simple this is. You know, I just store the bytes in an array list. And you can see I'm calling remove first to pull the very first byte out of the buffer, the byte that was, you know, in there the longest. And anybody who's worked on array list knows that remove first is going to be problematic, but this whole thing is problematic. For illustration, let's assume I've got like a buffer that currently has 5 bytes in here. I'm going to just paint my bytes different colors just to, you know, give them distinction. And I'm going to have some caller pass in 7 more bytes and say, hey, receive these 7 bytes. And so in that loop, we sort of copy the bytes in one by one. And then, you know, that process is done. And now my buffer holds all 12 of these bytes. And then some caller at some point in the future is going to say, hey, give me data. In this case, you can count there's 10 slots. And so the buffer implementation is going to copy these bytes in one by one. And it like looks slow and it feels slow because everything is happening a single byte at a time. And then we're left over, we've got 2 bytes left over, you know, from what is still available to read. This implementation, again, it's easy to get right, but it's extremely slow. If you're familiar with a whole bunch of Java memory semantics, there's like an auto boxing thing that's happening here. And there's just like a lot of work that happens in order to satisfy these calls. So let's do something faster. Let's do the buffer is a byte array. And so here's an implementation. The state, the field at the very top is the only thing that's really interesting here. We have a buffer, which is an empty byte array to start. And when we read or write things in, we're going to sort of like change that byte array. And so again, we'll start out with the same bytes. Somebody's going to come in and say, here's 7 more bytes, add these to the buffer. Java arrays are not resizable. We can't just like add data to them. And so what we do instead is we create a new buffer with enough room for both of them. We copy everything in from the first array. We copy everything in from the other array. We let the original buffer sort of array go out of scope. We're done. And then when the read call comes in, we sort of apply the same thing in reverse. We're going to copy all the data in that will fit. And then we need to sort of get rid of all of the other stuff. So we chop it off by creating another byte array, copying things in, and then letting that one go to scope. And so we end up in the same state we were in the other case. We've got 2 bytes left over. But this time, rather than going byte at a time, we used something like system array copy to move a whole bunch of bytes at once. In these examples, I'm doing 5 bytes. In your application in practice, this could be tons of data, like kilobytes of data. And so this one, again, it's easy to get it right, but you'll see there's lots of allocations. There's places where we're creating brand new byte arrays, using them, and then throwing them out. And every single byte in the system gets just copied around over and over again. And so this implementation wins on simplicity, but it's still relatively inefficient. We can do better. So let's do better. This code's more complicated, and you can see at the very bottom of this, I have an ellipsis because I've only been able to fit the write function onto screen here. And so you can see the most important part, again, is at the top of the screen. My state is a buffer, a position of the very first byte to read in this buffer, and a position of the very last byte to read in this buffer. And so I represent this visually as just 5 bytes in the middle of a bigger 16-element buffer. And I've got arrows indicating the position and limit of the first and last bytes. Now when the write comes in, we have a problem. We only have 4 slots left over on the right-hand edge. So we do a copy of the original bytes, forget about them. They're sort of still in that array, but we just don't have to think about them. Then we can copy the new bytes into place and move our position. And so we end up not allocating any new arrays in this process. That's really nice. And then when the read comes in, we copy data in. We can just slide our cursor and sort of ignore that other data. And so this approach is great because we're no longer allocating byte arrays every single time somebody wants to access our thing. So this is a slice of a byte array, and we're starting to get more sophisticated. You can see this is a lot faster. There's no allocations. There's a few things that are like obviously, bottlenecks here. And then one other factor that is a consequence of this implementation is that there's like dead memory in this example. So we have, even though we only need 2 bytes of data at the end of this, we're storing 16 bytes. And so you can see that like these different approaches have different trade-offs. So let's do a circular slice. This is something, you might have heard something called like a ring buffer. This is the same sort of technique. And here we're storing the exact same state, but we're changing how things work. So we're not necessarily just making it so that the arrays are always sequential. They can actually wrap around the end. And the implementation just continues to grow in complexity here. I've only bothered to keep the write function. It doesn't even fit on a slide anymore. And so here is my data in the middle of an array. When the write comes in, instead of having to do that shift and doing that, like all that extra work, we just write some of it to the part at the end. We write some of it to the part at the beginning. And then we have our start position actually after the end position in the array. And we just have business logic that says, when you're reading, you read from the start until the end, and it's allowed to wrap around. So that's how the circular array buffer sort of is written. And then reading it is very much the same. We copy data from this side, then we copy data from that side. We adjust the cursors, and we're in business. And we've got ourselves like a really nice, efficient solution. This is a lot more code. It's even more difficult to get right. And we have this nice constraint now, which is that every byte is copied exactly once. We copy it on the way in, and we copy it on the way out. Our buffer never shrinks. And we also, I didn't show the buffer growing. If ever we were to exceed 16 bytes in this example, we'd need even more space. So let's go into like a completely different direction. I'm going to talk about transferring array ownership. And this is just like a really weird left turn in strategies. Going all the way back to Java input streams, there's a fundamental need in these things to perform copies when data is read or data is written into input streams. But we can change the API and say, what if we don't perform copies? What if the object that you pass in is more sophisticated than a byte array? And so in this case, we're imagining some buffer type that you can read and write, where the storage of a byte array is not necessarily explicitly specified there. And I'm going to represent this as a byte array that's inside some like array list here. And so I've got my 5 bytes and it's inside of an array list. When the caller calls in and says, hey, I've got 7 bytes to write, it's in its own array list. And we do this cool trick where rather than copying the data, we just change which list it's in. And so our new state is sort of like the implied concatenation of 2 arrays, and we steal data from the inbound buffer. When the read comes in, originally we were always passed an array with 10 slots. Now I'm going to start passing a parameter that says I want 10 bytes. So we'll copy in the first 5 bytes in that first array, and then we have to split our buffer. And so we create a buffer with 5 slots and a buffer with 2 slots. We move 1 into place and we keep the remainder. And so this strategy is getting much more sophisticated, and you can see that we go from having to copy every byte once on the way in to once on the way out to potentially not at all. So, in this implementation, this sample code is like really simple. I'm not covering the case where we have to split the array, but you can see it fits on a slide again, and this is really powerful. In order to do this sort of transferring ownership strategy, we have to give up on the Java IO APIs, because we have to give up on the idea that like a byte array is both the physical storage and also part of like the API for sending data around. One of the problems with this specific implementation is that you can see that as we split the byte arrays, if we get them split too small, we get really bad performance. We actually get back to that sort of like array list performance at the very first implementation, because we end up just moving bytes one at a time between lists. So this has all been, a big fancy preamble to lead to the implementation of a class we originally called OkBuffer, which is the buffer implementation that we'd originally written to solve this HTTP2 problem in OkHttp. And so the idea of this is we fuse a couple of different ideas from the different buffers I talked about in this thing. We've got a segment, which is a byte array and a position and a limit, 2 different offsets. And then we have a list of those. And so the overall implementation kind of looks like this. We have an array that's oversized, just like in our sort of like our circular or slice example. And then that itself is inside of a bigger list. And so when data gets written, we can do that same technique where we just move it in, and that's really fast. When data is read, we can move some of it in immediately. And then here's like another magic trick that OkIO can do. That segment object has its metadata of like where the start is and when the end is. And then it has a backing byte array, which is the actual data. But we don't necessarily need to have 2 different backing byte arrays for 2 different segments. We can just, have 2 different segment objects that both point at the same bytes. One of them has the position for the first 5 elements. One has the last 2. And then, these are actually 2 different segment objects that share the same byte array, and we don't have to do any copying to split the buffer or to split the segment in half, or to split the segment, 5-2 or whatever. And so now we can move that around, and we get this sort of like best of all worlds approach where we take ideas from this transfer ownership model and from this array slice model. In OkBuffer, all of the byte arrays underneath are the same size. They're 8 kilobytes. My examples here, they were 8 bytes. I would need a bigger, I would need a higher resolution display to fit all, 8,000 and so bytes on screen. And then OkBuffer has 3 different ways that it efficiently moves data between buffers. It moves an entire segment at a time. That's really, really fast, because we're just manipulating ownership of data, but we're not actually copying it. We could copy data between segments. I think right now OkIO does this whenever it's less than a kilobyte of data to copy across. Or we can split a segment where we have 2 different segments that both point at the same underlying byte array. And this combination of techniques makes it so that OK buffer is really fast. And so pulling back and looking at like how we use this in OkHttp, this is all sort of like hypothetical sample code. But when we receive data, we just copy it into a buffer. And when we read it, we just read it back out of that buffer. This is like very simple to use. And the OK buffer class is doing all the heavy lifting. We built this. We were really proud of it. Hey, like, let's open source this. And like, it's kind of weird because OkHttp is already open source. But we thought that like we built something that was in service of OkHttp, but also, you know, unique and standalone. And so we released OK Buffer in the open source project. It's just called Buffer in our new library called OkIO. And so you can see the origin story of OkIO is we just wanted to take something from OkHttp, lift it up into its own standalone library. And that worked really well. I can't believe it's been 8 years since we did this. And so drawing back to that like original analogy of Java IO, same destinations, you know, data is going to files and sockets. But because we change to not use byte arrays as our fundamental transport, we have to create our own equivalent of input stream and output stream. OkIO calls these source and sink. And then the data that we travel doesn't go through byte arrays, but it goes through these buffers, which are just like a higher level abstraction on top of a byte array. So here's our interfaces, you know, read and write take buffers. And they also take a byte count, which is just how much data to copy from that buffer into the sink or out of the source. So now I'm just going to go through a few other things that are in OK Buffer. And one of them is kind of weird. It's zero fill. And so imagine you're writing some code and you say new byte array of size 8 kilobytes. What this does is it asks the memory management garbage collection part of your Java VM or Art runtime to free some memory for you and make it available for you, or to allocate some memory for you and make it available to you. And it'll create an object header. It will create the space that you need, but it also always hands you a fresh, squeaky clean byte array. And so before it returns, it actually fills every single byte in that byte array with 0. And as a consequence, creating an 8 kilobyte byte array takes 8 times as long as creating a 1 kilobyte byte array. This is like somewhat surprising, and it's not surprising depending on how much time you spent with like this low level of programming systems. And so what OkIO does in its buffer class is whenever you're done with a segment, OkIO recycles it into its private sort of queue of unused segments. And whenever it needs a new segment to put some data somewhere, instead of asking the VM for a new byte array, it gets one that's already allocated. And that process makes it faster because we don't end up spending time filling an 8 kilobyte array with zeros that we're never going to look at. And the fact that we've got this like position and limit, the range of the byte array that we're actually ever going to look at, those things mean that we don't have to worry too much about having garbage data left over in our byte arrays because that data is just not accessible through the API. One other thing that we can do with this approach is I'm calling it fast clone here. And so when you're using this buffer data structure, when you read data out of it, it doesn't just like move a cursor. It actually moves the data. And so as a consequence, reading data from a buffer in OkIO is destructive. If you read an entire buffer as a byte string, the buffer is like empty when you're done. And so what if you want to, have your cake and eat it too? What if you want to read a buffer and still have the original data in it? Well, you can just call buffer clone. And, that's a good idea, but how do we make that fast? Well, in OkIO's buffer class, in addition to the position, the limit, and the data, we also keep metadata on whether or not that data is shared with any other segments. And so in order to do a clone of a buffer, we end up cloning only the metadata and marking it so that the metadata on both the newly cloned buffer and the original that it came from is marked as shared. And what that ultimately means is it will prevent the buffer class from writing data in a place where the other buffer copy would ever see it. And it also, this just ultimately makes it so that when you call buffer clone, we copy the metadata, but we don't actually have to copy any of the original data. And so no bytes are copied. And so you can clone, an 8 kilobyte buffer really, really fast. And, you can also clone a, 10 megabyte buffer dramatically faster than it would be if you were doing it conventionally. One other thing that is sort of in this space is I've been talking a lot about buffers as things that just hold opaque bytes. But the things that make OkIO's API nice is that you can write not just the byte array, but any set of primitive types. A byte writes 1 byte to the buffer, a long writes 8 bytes to the buffer. You can write numeric types in sort of decimal or hexadecimal form for human readable things. You can write your strings, and you can even write the entirety of a source into a buffer, and that will just plow through the source, reading its bytes until it's exhausted. All these things also have additional overloads for little endian or for ranges. And then we have all the same APIs to read. And so your buffer class ends up being something where you can just write data to it, read data from it, and it just holds your data carefully for you. If you're coming from Java IO, one of the classes that's really friendly to use, sort of maybe the first classes you learn, is buffered reader, and it has this function it has a function read line. In OkIO, we call it read UTF-8 line, and it just reads a single line up into the next new line character or the end of the file. I love this API. I think it makes OkIO really easy to use. We also have a form that's strict, and this will not allow itself to be terminated by the end of the file. This is mostly useful to prevent a problem where if you read a file that's truncated, somebody sends you, a 5 kilobyte file and you only end up receiving 3 kilobytes of it. Reading it strict will mean that you'll usually not end up terminated by a new line and thinking that you've read a full line when you haven't. And then read UTF-8 line strict with a limit is really, really handy because you can prevent yourself from running out of memory by reading a 2 gigabyte file as a single line. And you can just specify, I'm willing to read this line, but I expect it to never exceed, 1,000 bytes or something. So this has all been buffer. I talked a little bit about source and sync, but we also have buffered sync and buffered source, which is where we sort of fuse the ergonomics of these reader and writer methods right onto the stream. And so if a buffer holds a fixed amount of data, once you read to the end of it, it's gone. Whereas a buffered source is a sort of unbounded stream, and you could potentially read it forever. And so you can read data from an ongoing retrofit API request. You could start reading the JSON before the JSON file is completely finished downloading. And so this is sort of a friendly ergonomic API over that source interface. Buffering streams is totally awesome, and you should always do it. It's got better usability. So instead of having to clumsily pass a buffer into a source, you just read whatever you want. It guarantees you to have good performance because you're always sort of moving data in larger chunks, and it has very little overhead. So when you use a buffered source, you know that OkIO buffers don't have copying in the middle. I want to blitz through 10 things that you can do as a user of the OkIO APIs. I've sort of thus far been talking all implementation details, and they're really fun for me. This is sort of where I've been having a lot of fun building this library and working with my teammates on this library. But there's also cool things you can do as a user. So I'm just going to go through 10 of them real quick. Streams have cool end of stream handling. So if you want to know how much data is left in this buffered source, you can either say, I would like to request 100 bytes, and this returns true or false if there's going to be 100 bytes there for you. And that will basically buffer 100 bytes to guarantee that they're there. It will wait until it can download 100 more bytes on the stream. And if it runs out of data before it gets there, this will return false. You can require 100 bytes, which is the same as requesting it, but this will throw an IO exception if the data is not there. And then you can say, hey, is this exhaustive? And this is really handy to use in loops where you can just say while there's data still left in my stream, while it's not exhausted, do some work. Peak is like a streaming clone. So in addition to reading our buffer and potentially cloning our buffer, buffered sources also have this function called peak, where you can read the entire stream more than once. And so the way you use it is you take your source stream, you peak it, and then that gives you an entire new buffered source that you can read as much as you want. And you may read, the first 5 bytes, or you might read the first kilobyte, but eventually you'll sort of learn what you wanted to learn. You can close it and then proceed to read the original source. This API is just sort of like a streaming clone where it just like adds, it clones segments as you progress through the stream. And it's fast and it's great for look aheads. We use it in Moshi to do looking up the type of a message. Select is really cool. So in addition to all those read byte, read long, read string functions, we've got this interesting one called select. And you have to prepare a options object beforehand. And so in this case, I'm preparing an object of 3 different byte strings. And then I can call select. And what this will do is it will look at the buffer and say if the prefix, in this case, is the bytes STAR, then return 0. If the prefix is PLANET, return 1. If it's MOON, return 2. And otherwise, it will return -1. And the consequence of this is when you're building libraries, you can avoid string allocation in your inner loops by just saying, like, these are the values I expect to see. What are they? And so this is really efficient. And it's also particularly the API worked out nicely. And if you see there's a select API in Moshi's JSON reader, it's built on top of this select function in Okio. You can read and write as Java IO streams. So, much as I've been saying Java IO streams are bad, all of the interop exists on top of them so that you can view a stream as an input stream, or you can view a sync as an output stream. Pipe connects a reader and a writer. And so there's a class in OkIO called pipe. And unlike buffer, which is not thread safe, pipe is, you can sort of have one reader thread and one writer thread. And so in this example, I've got a writer that's writing the first 1,000 longs and a reader that's reading the first 1,000 longs and summing them up. And this is just really nice because it's a particularly compact way to connect different threads doing different parts of work in your program. And we use this in OkHttp to do something called duplex. So it has a use case. I looked at there's a pipe class in Java IO, but it's particularly problematic because it's whatever size of the data is in the middle of the pipe, it will it has to be fixed and it will always allocate that. So if you want a pipe that can buffer a megabyte, it will allocate a megabyte. And if you ever exceed that, your code starts blocking trying to write to the pipe. Throttler slows things down. And I think I could just play this. A throttler is just a class that allows a certain number of bytes per second. And so in this program, I'm throttling a download in an OkHttp interceptor. And throttler is just something where I can say, this is how many bytes per second. You'd want to use this in your application if you wanted to say, like, prevent your service from denial of service attacking something that it was talking to. Cursors offer byte array access. So we talk a lot about how, like, buffer is this fantastic abstraction that hides the byte arrays underneath. Hiding those byte arrays underneath, most of the time that's really convenient, but sometimes you want to interact with somebody else's API, and that does something else. So in this case, my example is I'm talking to Guava's Murmur3 hasher, and it has an API that accepts bytes. Accepting an entire byte array is like really efficient. And so with Buffer's cursor class, we can get temporary access to the underlying byte array, and it makes sure that we sort of access the right parts of the underlying byte array, and we don't go out of bounds. Timeouts work everywhere. This is a really fun example. So OkIO comes with a timeout class, and it just sort of configures how long an operation can take before it's supposed to be killed. And we have an implementation called async timeout that has a callback timed out that tells you, some operation is still happening. Go kill it, please. And so in this case, even though the timeout class is sort of like associated with OkIO and it comes with OkIO, you can use it anywhere in your program. And so in this case, I'm creating a process builder and then I'm running it for 5 seconds. And if it runs for longer than 5 seconds, I call process destroy forcibly, which is like kill mining the process. And this worked really well. I ran this example and it like pulled 5 seconds worth of data from my find command, and then it failed with an exception because it timed out. Byte string. So I'm 2/3 of the way through my OkIO talk, and it's time to finally reach byte string. Byte string is just like buffer's mutable friend, or buffer's immutable friend. And byte string is really, really handy whenever you just want to store opaque data. And so in this case, this example, I'm taking an OkHttp response. I'm just copying the entire thing into a byte string, and then I can pass that around like a value. It's nicer than a byte array because it's immutable. And then it has a whole bunch of things that sort of like work like values work. Like it has an equals and a hash code function that work the way that you expect byte code, that you expect to work, instead of the corresponding functions on byte array, where equals and hash code of two byte arrays with the same contents are not equal. So byte string is really like just a nice, easy value class to have. Last one in my 10 cool things you can do with OkIO. Hashing can be really easy. So if I happen to have a byte string somewhere, or I can just call SHA-256 or HMAC SHA-256 or SHA-1 or MD5 or any of these things and get the hash of the data. And so in this case, I pulled some example from one of the services we're working on, where we're getting webhooks from GitHub, and we just have to say, like, what's the hash of this data? It's really not a big exercise. And I found this just to be really refreshing compared to the corresponding APIs in the Java SDK, where I have to pass hash functions as strings and defend against the fact that like those may not exist, where in practice they always do. So those are our 10 cool things. I want to just rip through a whole bunch of other cool stuff, nerd out on more cool stuff in OkIO. We've got a file system in OkIO 3. Just like, why the heck would you build OkIO? Another question on that is like, why the heck would you build a file system abstraction? That seems like a lot of work. Well, for us, we were using a lot of Kotlin multi-platform, and Kotlin multi-platform needs a file system. We didn't have one, so we put one together. If you ever try to use like Java IO file or Java NIO file.path, you'll see that like those APIs just really fight you if you try to write tests. And so we thought we could do better. One of the things that was like really difficult about this was just like actually doing multi-platform at the level of a file system was really hard. I had to spend a lot of time learning, and my teammates had to spend a lot of time learning the like the Win32 files APIs and figuring out like what the differences are between POSIX on Linux versus POSIX on Mac OS. And there were differences that we ran into here. And then trying to make everything everything testable. The one other thing I think is interesting here was just like, it was really difficult to figure out what's included and what's not included. We definitely don't let you say like, how much space do I have left on this disk? Or, I like to subscribe to the watches list on this directory. We left those out for simplicity. We sort of like went for what do most Android applications need most of the time as sort of like the litmus test. The one feature that snuck in that worked out well is symlinks. Here is an example of using the file system in its sort of like best case. And you can see that you always need an instance of file system. There's no sort of like static global file system object that we give you. You have to like have one. And then if you want one, it's just file system dot system for the sort of like the canonical one on your machine. That all works relatively well. And you can see that inside of those read and write functions, the receiver is a buffered source or a buffered sink. And so you can call functions that we saw earlier, like write decimal long or exhausted. Some things that worked out really well in our file system. The fake file system is fantastic. You can simulate a Unix file system on Windows or vice versa. You can open a zip file as a file system. You can open your sort of class path resources as a file system. And all of those things together sort of mean that like anywhere you want to access something as files, you can do it uniformly. Okay, so OkIO is going great. I want to talk about a bit about some of the regrets that we've had. We screwed up the names. So we've got this class buffered source and buffered sync, and then we have the other classes source and sync. And I regret that we gave the worst name to the more important class. I think that it would have been nicer if we would have called the bigger one with the more functions, if we would have just called that source. And then maybe like the one that has a tiny number of functions, we could have called that like raw source or something like that. Another thing we could have done better is every source and every sync has a timeout, but I think that it might have worked better if they just were cancelable. There's a library called Trio for Python that does this, and it just works out so much nicer in practice. Our timeouts effectively do cancel when they run out, but cancel is just sort of like a more powerful primitive. We've had our share of controversies building the OkIO project, and I want to talk about a couple of them. Why the hell is OkIO a blocking API? In Java, especially on the server, there's just been a big trend in the last 10 years to make everything completely asynchronous. Anytime you're talking about Java server things, it's all about, Netty as a particular implementation of asynchronous IO. And, it's just like how things are done on server. But in OkIO, everything is blocking like it's the 90s. What the heck is the difference between these two things? Non-blocking is a cool feature for horizontal scalability where you can have one web server with like 100 threads simultaneously serving 10,000 different concurrent calls. That's just a real superpower to have in your service, especially if you're running something like a WebSocket server where you're talking to all those clients, but not all the time. Non-blocking is not otherwise faster than blocking. It's just merely more scalable, and it's particularly more scalable once you get beyond 100 concurrent IO operations at a time. The other side of it, though, the flip side of it is that in order to make that non-blocking thing usable, you need abstractions in order to sort of encapsulate work and to move it between threads. And then you also have the cost of context switching between threads. So as a consequence, we have this bug report. This is my favorite bug of all bugs in all time, which is a bug against Grpc Java. And it says Netty is significantly slower than OkHttp. Grpc Java, as background, has both a Netty backend and an OkHttp backend. Conventional wisdom says the Netty one should be faster, and it's reported as a bug that it's slower. A bunch of really smart engineers spent a lot of time trying to make it so that the Netty one was faster, but the fact that this bug is still open 2 years later is because OkHttp continues to be a faster strategy for implementing Grpc clients. And it's sort of like validation that like blocking isn't the end of the world. There's also this thing coming in a future version of Java, maybe Java 21 or 22 or something, called Loom. And the hypothesis of this is, rather than doing all of this work to make everything asynchronous, what if we just made it so that that fundamental problem we were solving with async, which is that threads are expensive? Why don't we just make threads cheap? And so Project Loom is making threads cheap. They're building this thing called virtual threads, where it's just you can create thousands or tens of thousands of threads just the same way you can with coroutines in Kotlin. And this is already in preview, so it's like very much on the verge of just coming to all Java servers. You'll also see that OkIO is not suspending, and there's a cost to doing suspend functions, because if you look at what happens to your suspending code, the Kotlin compiler rewrites it into this little state machine, and that has a cost in terms of just how much code there is and how much time it takes to execute. And so what I recommend you do in OkIO is absolutely do suspending, but do the suspending in a higher level abstraction, like in retrofit or wire or coil. One other controversy we've had in OkIO is that we changed this library from being implemented in Java to being implemented in Kotlin. 2018 we did this. It was like, just at the point where like Kotlin was becoming pretty mainstream. And Java programmers, saw this and said, what the heck? They'd all been burned by libraries that had dependencies on like the Scala standard library, the Grpc standard library. And so seeing one of the libraries that they liked converting to Kotlin was something that they were sort of necessarily nervous about. B-Side Up, or Sergey Egorov, who runs the awesome test containers project, tweeted around the time that we did this, oh no, one of the best HTTP libraries with JVM is going away. Like for him, the idea of us converting to Kotlin was the same thing as us just not existing anymore. And so, that was a real controversy. But we got no regrets. I think that, years later, having already converted to Kotlin, Kotlin's been so good to us. It's been like so much more fun to work on these projects. And it's created a lot of opportunities for us. We can do things in OkIO with multi-platform. You saw that like multi-platform file system. And, we're looking at moving OkIO into lots of new places to solve more problems. The other thing is that like a lot of those fears around things like, will it work? Will it have the same problems that Scala had or that Groovy had, where the Scala library changes and I can't upgrade? The Kotlin maintainers have just been really serious about backwards compatibility, and it's really helped for us. So I've been nerding out about OkIO, and I just wanted to wrap up. OkIO is healthy, stable, and the happy kind of boring. I hope you enjoy using it, and thank you to Android Worldwide for hosting me. Yeah.
Sweet. Wow, you actually pulled it off in the time limit you wanted.
You could see that I was doing variable speed of speaking.
I mean, you didn't pause very long for drinking either. So that's,
yeah,
I feel like that's the key, Yeah. Oh, you got to have bubbly. Okay. Yeah. That'll wet it.
Got to represent Michael Bublé.
Folks, let's give you another minute to write any additional questions and upvote questions that are already there that you like. Big thank you to Jesse for that wonderful presentation. It was kind of like you took us on this ride of, okay, like here's the start of this concept, and okay, so a bunch of people probably have some questions, and then you make your way to answering all of them, like right near the end. And I'm like, shit, there goes like all the things I wanted to ask about. Now I look like a fool. I have no questions. No.
Hopefully.
No, that was great.
Should I just go through these?
Let's give everybody another like 30 seconds, because I just want to make, because once you start answering questions and people are trying to write them, it gets uncomfortable. Yeah. All right, sweet. So you just put yourself as in Canada. So you represent all of us.
Yes.
All right. 10, 9, 8, 7, 6, 5. Let's go. I think we're good to go. You just start reading the question and I'll show it on stage.
So Martin says, zeroing out arrays after sensitive data was in them is recommended as a security practice. Can I do something with OkIO? So this is like admittedly difficult in OkIO because we try our best to make it so that like you just never see the data that was in your arrays. If you're in this kind of situation where you can't have this kind of data in memory anywhere, there's like limited things I can tell you. The thing that we have that comes closest is that you can use that cursors feature to get raw access to a byte array. Unfortunately, because of the way OkIO works, we're doing lots of things behind the scenes to sort of like create other segments that have access to that original byte array. So it can be difficult to do. It's something that's probably worth opening up as a tracking defect on OkIO's issue tracker so that we can think more deeply about it. But right now we don't have any way of like tagging a buffer as sensitive, and then like that would be a feature we could build where we could shred it after it's done being read. Effaturi writes, are there benchmarks comparing OkIO versus Java NIO, which is faster and under which circumstances? we generally don't benchmark things at the layer of OKIO or NIO or Netty, often because the benchmarks would be too fake. We want to do real interesting work, and so the layer to do benchmarks would be at the layer of like an HTTP call, or even better, like an end-to-end REST call or a Grpc call or something. The best benchmark I have is that one I alluded to with Grpc Java comparing Netty and an OKIO based backend that they're using, and that shows that like sort of like strict QPS, the OKIO one is faster for that particular benchmark, but it all really depends on interesting things like access patterns. We've been doing benchmarks of things in protobufs for our Wire project, and we find that like certain things appear really fast, and then you start like interacting with objects, and the things that were fast turn out to just have been lazy. And so you might find that like if you're using certain APIs in benchmarks, your benchmarks may not be representative of production, because the benchmarks may not actually do all the work, and these IO libraries love to take shortcuts where they can defer work as much as possible. Benoit writes, any cool upcoming feature or improvement you're hyped about? Your timing is fantastic. So as of like an hour ago, we merged support for Kotlin hierarchical projects. And what that allows you to do is, rather than when you're building against OKIO in a multi-platform project, rather than being sort of stuck on what's in the common, sort of like the common main directory or the common platform, you can call any API that's available in all of the platforms that you're currently targeting. And so for OKIO, what that means is some of the features we have are available on iOS and Android, but not available in JavaScript. And so previously that was a huge hurdle. And with Kotlin hierarchical multi-platform projects, that problem is solved. You're going to need Kotlin 1.6.20. And once you have that, you can upgrade to forthcoming OKIO 3.1.0. And that is going to be rad. And that's another thing where the team at JetBrains has just been, completely crushing it and making us really happy that we're on the Kotlin platform. Efiteri writes, is there any non-blocking IO? What would they look like? Did OKIO ever consider non-blocking IO? I talked a little bit about this in the presentation. The most interesting thing is it sort of comes as the form of some kind of callbacks. Medi writes, does OKIO replace OkHttp? These two libraries are complementary. If you're using OkHttp currently, you're sort of like also using OKIO. You might not even notice it. OKIO is like a little IO engine that sits inside of lots of different higher level libraries. And so inside of OkHttp, it's doing all the sort of like data buffering stuff. It's also working inside of Moshi and inside of Wire, and also inside of Coil. Nicola writes, do you use object pools for segment object recycling, or do you use something else? I don't think we use any formal like segment pooling. We don't use any formal object pooling API. We wrote our own thing. I wrote a blog post about this on publicobject.com about us making changes to how our pooling works. We used to have just a sort of like something like an array list that's backed by a synchronized statement. And so whenever you're done with a buffer, you will take a lock on the array list and add, or when you're done with a segment, you take a lock on this array list and then add your segment to that array list. And then whenever you need a segment, you take a lock on this array list and then try and see if there's any elements in it. We recently made a change to OKIO around massive concurrency and contention, where instead of having like this sort of like simple synchronized system, we do something where it's more like a striped lock. And that means that there's a lot less contention. And this was very valuable for applications that are just like sort of continuously putting something in a buffer and taking it out, and putting something in a buffer and taking it out, because there's no longer contention on the locks. And that code was really fun to write. You know, I was talking about OkIO being fun. There's just been a lot of places where it's like, we have something where like we have the simplest code that we thought could work. And now we've got a real world use case from somebody who says, hey, I found a bottleneck here when I put this thing under like extreme pressure. And then we get to spend some time and like learn a whole bunch of stuff about memory models and concurrency and build a solution for that. Epituri, for the streaming clone, does closing the clone unset the shared flag? So as soon as you clone anything, if you do a peek or a clone, it sort of like is, once it's become shared, it's shared forever. And this is just an implementation optimization that keeps everything really simple for us. The only real consequence of having that shared flag set inside of the buffer is that when you go to write to that segment, only its owner is allowed to write to it, and none of the other threads will ever see that data. The other consequence is I don't believe we pool segments that are shared, because we don't know when the last buffer is done with them. And so that's basically us saying like the benefit of pooling is somewhat negligible, and we just like let the garbage collector do the work instead of us having to do like manual reference counting or something like that instead. Jeff Coran says, when will you attend the next Android social night? And I suspect he's talking about the Android social night in Kitchener, and it's tonight, and I will be there, unless he's talking about the one in Toronto, in which case I'll be at the next one, and it will be merry. That will be really fun. Shalom writes, the comparisons focused on OkIO performance in the Java ecosystem. How does it perform for Kotlin native and JS consumers? That's a fantastic question, actually. And to be completely honest, we haven't really spent much time tuning for Kotlin native or for JS. And so that is an open question for us. We've been mostly concerned with like correctness on those platforms, and getting into the point where we're like, you know, measuring OkIO against whatever the sort of like platform native thing is on native would be really fun. Also potentially quite challenging, just in that like we're making lots of assumptions about how JVM things work. And so maybe that's the sort of like opportunity to go nerd out on stuff, is trying to make those things faster. Last one, Christian says, is there a plan to support writing a zip file in OkIO? Nothing currently. There's already lots of different JVM APIs to do this, and I find this use case to be something relatively rare, that like I don't think we would add anything particularly valuable there. But if you got a use case, write it up on our issue tracker, and we will certainly consider it. I think there's like I think there's like no real reason to not do it, but it hasn't come up for me, and so I'm like a little biased against something I think might be otherwise rare. All right, that's all the time I have for questions. Thanks for all the questions. Those are really thoughtful. And thanks to Android Worldwide for hosting this.
Yeah, there was one more, but if you got to go, you got to go.
Oh, well, this is one more. Did I miss it?
Yeah, I guess.
Oh, cool. How big is your test suite? Give the libraries translately used by so many projects. How do you make sure it never breaks? Martin, you know how big our test suite is. It's big enough, but it's not big enough. We generally write like lots of unit and regression tests for all the different features, and then we use parameterized tests to make it so that we can guarantee that all of the 99 different ways that you can like have something that implements the buffered source interface are all working consistently. So like we might have a buffered source that's backed by a buffer or by like a regular stream, or we might have one where the underlying segments are all tiny, and that's like a thing that happens that like potentially exacerbates certain use cases. And so I'm comfortable with the level of testing that we have. And I figure that one consequence of being in so many projects is that like we will easily pass the scream test. Whereas if we introduce a regression, people will scream and we'll find out about it very, very quickly. That hasn't happened. But I know that people have shaken out very, very like corner case bugs in OKIO by saying like, hey, if I do this thing and then that thing and the other thing, this doesn't work the way I expected it to. And so it's very, very well exercised, and that makes me feel like it's mature, and our test case gives me lots of confidence to make changes. Cool. Thanks, everybody.
All right. Thank you, Jesse, very much. We're going to